As we do the textbook background on topic 1.2, Algebraic Expressions and Sets of Numbers. So again, the objectives over here, and this is what we'll take a look at. Again, I'm not going to read everything. You can pause and read if you like, or of course go to your online textbook. So we want to look at what is called an algebraic expression. Well, in algebra, in mathematics, we have letters, often the X. We use the letter X as a variable. This could stand for something in an algebraic expression. So as we look at these, separated by commas, these are all algebraic expressions. And as we look to develop what is being done there, let's take a look at our 2x. Well, what does this mean? 2 times x. When there's no symbol between a number and a letter, it implies multiplication. And sometimes they use this down here. Now, if we're going to add, we have to put a plus there. And if we're going to subtract, we have to put a minus sign there. Now, this is a horizontal division bar. And when you write fractions, this is how you should write them, horizontally. This bar also is a grouping symbol, indicating all of what is on that division bar. Now, the upper part of a fraction is the numerator. This bottom part is the denominator. Now, this is what we call a radical sign. You often heard the words square root of something. And a decimal, of course, we put down at the bottom where the multiplication dot is in the middle. And this is what we call something to an exponent. And we'll be going into some detail on that as we go through the course. So let's take a look at an example. We'll start off easy, that they're saying that in the year 2009, they said it cost about 45 cents per mile to drive a car. Then if you took that figure of what it cost and you times it by the miles, which is what our M is going to stand for, you get the total cost to operate a car annually for M miles. There's a nice little red car. So, to find the cost of driving 12,000 miles, what we would do is say that M is 12,000. So we now replace the letter M in this little item up here, that expression, multiply it by what it costs for each mile, and we get that for owning a car for 1 year cost someone $5,436. Okay. Now, the pattern of this algebra book is they give you some background, then they'll give you an example. And the nice thing about the textbook is if you follow, they're also going to give you the solution. But we want to know a pattern of how to get things done. So let's take a moment to read this and then take a look at how we solve it. So this company is producing tiles that are in the form of a parallelogram, means the opposite sides are parallel to each other. And the formula for finding the area of a parallelogram is area equals base times height. And they're going to give you what they are. The base is 10 and the height is 8.2. So you just substitute. The base is 10 times 8.2, and you get an answer then just by moving the decimal place over. 82 centimeters square. Now often they give a practice example, but they don't give the solution. We won't do them all, but from time to time. Here we're talking about a triangle, and the area of a triangle is a little different than this. It's 1/2 the base times the height. So they're saying the base is 3.5, and we have to put that in parentheses, and the height is 4. Well, I should say 8. I'm already doing something. Now for something like this, when we have factors here, we can actually do some cancellation. We can go, this is 1, and 2 goes into 8 4 times. So we would go 4 times that, and we would get 14 centimeters square. In example 2, we're looking at this expression, which I've written here, and we want to put in a value for x of 15 and a value for y of 4. So x is going to be 15, so I'll just do some fancy stuff here, and y is 4. So we go 3 times 15 is 45 minus 4, and that leaves us with a 41. And again, if you were writing this on your homework log, you would copy the example down, show the substitution, and then your answer. Now, another thing they're illustrating here is when you are evaluating an expression to solve a problem, you need to think about the kind of answers that you're going to get. For instance, if they were to ask you, how many parking spaces could you get out of a parking lot? And you ended up with an answer that looked like this. Well, you wouldn't put the 1/10 there because that's not a parking spot. So a little something to be careful about. Okay, now for objective 2, we're going to take a look at identifying common sets of numbers. And for this, we're going to take a look at the number line. If I were a student and I were reading this and I had my notes to the side, I'd start writing some of this down, because seeing and reading and then thinking about it and then writing it down is a way to help get something from short-term memory into long-term memory. Okay, so on a number line, they have a nice one here. There's my little sketch. We have a 0 that we can think of in the middle. This is often referred to as the origin. Now, when we go from a 0 to 1 unit, to the right of 0, this we say we've counted 1 unit. And to the right are positive numbers, and to the left of 0 are negative numbers. Now, one of the things we do, and we're going to introduce what we call here shortly, sets of numbers. One of our first set we'll get to shortly are the counting or natural numbers. Counting or natural numbers, and they're going to tell us that we can graph counting numbers on this number line. And we do so by just putting a dot right there. That's our first counting number. And there's our second counting number. And if we had a third number there, we could put that there. And to indicate that this pattern continues, we just darken this arrow. That indicates the pattern continues. And we see it here. They have darkened or put spots or made dots on 1, 2, 3. Now they also use this little helper, in a sense, these 3 dots that are referred to as an ellipsis, that indicates that this pattern is continuing. Now, again, these are the counting or natural numbers, and this is a way to write it in what we call hit the wrong button there. There, it's called roster notation. Notation is just a way to write something. So the natural numbers in roster notation, we use a brace and list them. 1, 2, 3, ... which is our ellipsis. Now on graphing, we show the ellipsis by making the arrow a little darker on that side. Now our next set of numbers, we'll call that the natural numbers n, are the whole numbers. And you might say, how are they differ? How do they differ? Well, the whole number, we just add a 0 to it, which is what they're showing here. And again, in roster notation. Now, if we go to the other side of 0, the origin, and we take the opposites of our whole numbers, it introduces us to the opposite of a 1, which is a negative 1. The opposite of a 2, which is a negative 2. The opposite of a 3, which is a negative 3. Now, when we have whole numbers and their opposite, we have a new group which we call integers. And where do integers go to? Well, we haven't said it yet, but way out there is negative infinity. And on the positive side out there is positive infinity. So what is written inside roster notation are members or elements of our set. And a set is a collection of objects. And as they mentioned, it's roster notation that we're writing them in. Now, another notation that we have, and you need to take notes on this, is what we call set builder notation. And set builder notation looks like this. And you have a brace, and it's read, x is such that, that's that vertical line, x is a natural number less than 3. So if you put that in roster notation, it looks like so. Now, sometimes they'll say something, but there are no members of that group. For instance, let's say natural numbers that are negative. Well, we just said natural numbers are positive. they're the counting numbers. So there are no negative natural or counting numbers. So that set would be called an empty set since it had no member. A synonym for it would be a null set. And an empty set could be symbolized by just making brackets with nothing inside, or I should say braces, or using a circle with a line through it. Okay? And an empty set, another example would be in set builder notation, X is such that X is a month with 32 days. Well, there's no month in our calendar that has 32 days. So that would be a null set or an empty set. Again, these would be things you would include in your notes so that you know the vocabulary of what's going on. All right, let's look at example 3. Write each set in roster form. List the elements of each set. X is such that X is a natural number greater than 100. So you put your brace, greater than 100, 100 is not included, so you start with 101, comma, 102, comma, 103, comma, and then you can just use dots, your ellipsis, to indicate that pattern continues. Now you could have put 104, but once the pattern is set up, the ellipsis indicates it continues, and it would continue in this direction to positive infinity. Now in letter B, let's see what they're asking. X is such that X is a whole number between 1 and 6. So if it's between, 1 is not included, 6 is not included, so we go 2, 3, 4, 5 and use braces. Okay, they do give us some practice, but we'll pass that up. Now, some more background and useful tools is this symbol. It looks like sort of a funny kind of E. This symbol, which looks like that printed, reads is an element of, or we could say is a member of a certain set. So 3 is an element of this. A way to write that in mathematical shorthand is to use this symbol that means is an element or is a member of. We prefer the elements a little more formal. Now, if you put a slash through it, that is read is not an element of. So as we look here, P is not found in this set. So P is not an element of this set. All right, let's go on to example 4. Now we are asked to determine whether each statement is true or false. 3 is an element of a natural number. That's set, and that is true. 7 is not an element of this set. Well, 7 is not there, and it's not an element, so this is true. How about this? 7 is an element of a natural number. That is true. 6 is not an element of this set. Well, 6 is not present, so that is true. As we go on in our textbook, they're saying we can use set builder notation to describe 3 other common sets of numbers. Now, all of the numbers that are on the number line are what we call real numbers. And so far we've identified integers. Well, let's start off with natural numbers, whole numbers, integers, and you notice we've sort of left out the fractions. So when we include natural numbers, whole numbers, integers, and we start bringing in fractions like 1/2 and fractions like 1/3, and we can go like 3/2 here, which would be 1 1/2, and fill in all these nice fractions that we have. We're going to introduce what we call rational numbers, and then we'll introduce irrational numbers that we have over here. Now, if we take 1/2 and convert it to a decimal fraction, it goes 0.5. This is 1/2. If we take 1/3 and convert that to a decimal fraction, that's 0.3. And in your calculator, the 3's will keep repeating. And we usually put a bar over the repeating part. So any decimal fraction that we get from this type of fraction, when we convert it, that terminates or repeats, is called a rational number. Now, over here, and I'll change color, right about between 2 and 3, let's see, no, 1 and 2, right a little bit before 1 1/2, we have the number, the square root of 2. Now, the square root of 2, if we were to write that out, it goes 1.414, and I forget all the others. I went to my calculator, and this is what I got when I put the square root of 2 in there. And notice it's 41421356 2, and in a sense it doesn't terminate. That's as far as it can go on the calculator screen, but it doesn't terminate. It keeps going on and on and on, because it doesn't terminate and it doesn't have a repeating pattern. We call that kind of numbers that make up their set irrational numbers. And any number under the radical sign that's not a perfect square, like 4 or 9 or 16 or 25, these would be irrational numbers. Now, they are on the number line. They just don't terminate or repeat. Another famous one up over here by 3 is pi. That's irrational. And later in math, you'll get the letter E, they call it. It's between the 2 and the 3. That's irrational as well. Okay, so this gives you some of the background, and this is what they're describing down below here. Now, some other interesting things is that when we see the number 3, actually that 3 is over 1. Every number is over 1. We just don't write it. Even 0 is over 1. A -8 would be over 1. Okay? So every number is over 1, but by convention we don't write the ones in the denominator. All right, so let's take a look at some of these. So over on the left we have rational numbers. Over on the right, some irrational examples. So again, anytime you have this radical sign, and it's not a perfect square under the radical sign, like 25 here, even though it has the radical sign, it's saying take the square root of 25, which is 5. And in a sense, that's 5 over 1. And once again, as you read your textbook, they do give you very thorough explanations and examples, things that we've talked about. Now, another sign they're introducing here is this sign where it looks like a capital C, but has a bar underneath it like so. This is the sign to indicate is a subset. So if we were to say that Z would be integers and Q would be real numbers, we'd say that Z, the integers, are a subset of real numbers. Remember, all of the numbers on the number line are real numbers. So all those subsets that we spoke of, natural numbers, whole numbers, integers, rational numbers, irrational numbers, are all a subset of real numbers. And they give you this nice little chart in summary. So I'm not going to go through this, but keep in mind this is in your textbook. Notice what we see here are usually very similar to the kind of practice in Quiz Me and test items that you will have in Math Lab. Here we want to see, are these statements true or false? And again, if you were writing this out in your homework log, I would expect the statement written, not just the word false or the word true. So 3 is a real number. That's true. 1/5 is an irrational number. Now the decimal of 1/5 is 0.2. It terminates, so this would be false. Every rational number is an integer. Well, integers are whole numbers, and they're negative opposites, so to speak. So there are many rational numbers that are not integers. So this is false. Again, you only have to find one example that proves it wrong to make it false. Now, 1,5 is a subset of this. Well, 5 is there, but 1 is not there. So this is false. Another part of our vocabulary is absolute value. Well, absolute value, and it's written with 2 vertical bars, and you'll have, let's say, a -3 in there, and you might have, let's say, a 5. They're saying the absolute value of -3, the absolute value of 5, and what these are is the distance that something is from 0. So when you count from -4, you count 4 units. When you count to +4, you're counting 4 units from 0. So the shortcut rule is that when you are taking the absolute value of something, it's always its positive value. Now the exception of that, it's not really an exception because this part is true, is if they have a negative sign outside the absolute value operation. So the absolute value of 5 is 5, but then we apply the negative to it, so this would be -5. And if there were a negative sign here, the absolute value operation is a positive 3, then we apply the negative sign, and that's a negative 3 here. Okay, so as we do these, it's quite obvious. This is going to be 3. This is going to be 1/7. Now here it's tricky. Comes out as a 2.7, but then we apply the negative that's outside. So this is a negative 2.7. Again, it comes out as an 8, then we apply the negative, and this is a negative 8. So this is the tricky part right there. Now, if you had your textbook, and if you clicked on this, actually these would show you little videos. And the absolute value of 0 is 0. And you might say the absolute value is always positive. Well, the one exception is that sometimes, well, the absolute value of 0 is 0. And 0 is unsigned. It doesn't have a sign. It's neither negative nor positive. Okay. All right, toward the bottom of this page, we have another little task, finding the opposite of a number. Well, by definition, the opposite of a number is what we would add to it to make it 0. That's its opposite. So it's nice to have some things that are easy. So the opposite of this is its negative value. The opposite of this is its negative value, because adding these together give you a 0. Now the opposite of a negative 4 is a positive 4. And another way to write this is the opposite of A is a negative A. They're giving you this as sort of a rule. Now an interesting thing happens when we have something like this. If there's a negative sign in front of a value that's inside the parenthesis as a negative A, we're saying the opposite of a negative A is a positive A. We often hear the expression 2 negatives make a positive. So the opposite of negative 4 is 4. The opposite of negative A is A. When you see this arrangement, the 2 negatives make it a positive. This is referred to as the double negative property. Now, for example, 7. We have the opposite of an 8 is a negative 8. The opposite of 1/5 is a negative 1/5. And the opposite of a negative 9.6 is a positive 9.6. And these, again, just change the signs, the opposite. In our textbook, they're going to give, again, much more background information. When you are writing phrases as algebraic expressions, when we do the operation addition, these are many of the common vocabulary words that indicate addition. These are for subtraction. This is for multiplication. And this is for division. Now, again, you might recognize these, or you'd like to take time to copy them into your notes somewhere, but we'll be using them, and you'll be getting practice as you do your math lab. Study plan. 8 times a number, and they're going to use X. So 8 times a number. We don't need a sign. 3 more than 8 times the number? Well, there's 8 times the number plus 3 more. The quotient of a number and negative 7. Well, we put it as a fraction. X over negative 7. This is a quotient. So put a little star by that. They ask you to write a quotient. The first part of the quotient is the numerator. The second part is the denominator. 1 6/10 subtracted from twice a number. So this would be twice a number, and you're going to subtract 1 6/10. 6 less than a number. X is the number less 6. Twice the sum of a number of 4 and a number. Well, we're going to do twice. Now, to indicate the word sum, this is the tricky part. We have to put it in parentheses to show that this is a sum. So I could put x plus 4, or I could have put 4 plus x. Either way. And I see that's how they're writing it. That's fine. And just for a little more practice, we'll do these. The product of 3 and a number. And we're still using x. 5 less than twice a number. Twice a number and 5 less. 3 5/8 more than a number. There's the number plus 3 5/8. The quotient of a number and 2. The quotient of a number, remember the first part goes on top, and 2. This is a quotient. 14 subtracted from a number. There's our number, and we're subtracting 14. 5 times the sum of a number and 10. 5 times, and then the parentheses to indicate our sum, a number and 10. Now, if you don't have the parentheses, we don't know that that's a sum. Okay, now they give us a vocabulary check that we'll pass up, but these are the words we use throughout our first real math lesson. And good luck to you.